welcome to Chapter 4, Section 7. In Chapter 4, we've been talking about applications of differentiation, and we are now going to talk about some optimization problems. And the format of this video will be me going through and looking at the slides provided that go along with Stewart's Calculus Early Transcendentals 8th edition. And after that, I'm going to toggle over and talk through not as many specifics as usual, I don't think. Although, I do tend to get off track and really dig deep into some of these things. But my plan is to just talk through the broad strokes of the approaches that you're going to be using to solve the optimization problems in some homework assignments, or rather, the homework assignment that I'm giving to my students pertaining to the topics discussed in these slides. So, if you would like to jump forward in the video and just look at those example problems and talking through the solution processes, you're welcome to. Otherwise, we're going to be doing pretty much the same thing in these slides, except the slides that we're looking at here already contain a lot of the solution process. So let's see if we can make this relatively quick. I'm going to challenge myself. So in optimization problems, there are some ideal kind of steps, or there's an ideal approach to solving these. And optimization problems are applied problems, are word problems, essentially. And the word problems that we see are often, they seem kind of silly, and I'm never going to have to fence in my backyard on my piece of property that's adjacent to a stream or a river, so I don't need to fence in. But three out of 4 sides of my property, that's not realistic. Don't worry about the reality of the problems. It's the process that we're trying to practice so that when you end up with other challenges, you'll have something to use to march through those new challenges. So understanding the problem is certainly important. Identifying the unknown, that is probably what will be designated as a variable or variables. And there are undoubtedly going to be some known values, the given quantities. And what are the given conditions? So are there any restrictions? In that fencing example, what kind of raw materials do we have to work with? So being mindful of all of those things is important. I am a big fan, as some of you know, of drawing a diagram. Even though my diagrams can look a little rough, they can still be very valuable, particularly if you're labeling your diagrams well and putting the given and even the unknown information, some variable labels, on your diagram. Introduce notation. So use good variable names if it's length times width, if it's height, if it's velocity, if it's speed, maybe use v for velocity instead, t for time, etc. And the value that we're going to target, here the author is talking about it as being your Q value. So whether you're trying to maximize volume, trying to maximize speed, profit, whatever the quantity is that you're going to be trying to maximize or minimize, perhaps, that is going to end up probably being the name of your function, or you'll end up isolating that value, because very often we're going to be taking a derivative, or sometimes a second derivative, in order to maximize or minimize whatever the targeted value is. So let's look at example 1 that's given to us. I knew this was coming. It's talking about fencing something in. A farmer has 2,400 feet of fencing, so those are our, that is sort of our restriction, and wants to fence off a rectangular field that borders a straight river. He needs no fencing along the river. What are the dimensions of the field that has the largest area? Now, if you've worked problems like this before, the approach that this particular author uses is maybe not the one that you would use, but for those of you who have not worked problems like this before, or at least not worked them in a calculus setting, let's have a look at some possible configurations or different ways that we could be using our fencing. So in each one of these diagrams, you're seeing that we are using a total of 2,400 feet worth of fencing but you end up enclosing these different shapes. They're all rectangles, but the one on the left has an area that is not as large as the others. The area in the middle, total of 700,000 square feet, and over on the right only 400,000 square feet. So it's obvious that the shape or the length and width of the area is going to have a big impact on the enclosed area or total square footage. So length and width here are being labeled as x and y, even though x and y aren't really, I don't know, they're not really great labels, right? You could have called them L and W at the very least, or actually written them out as length and width, but as long as you're labeling the diagram, you can always glance at the diagram and see what the variables are representing. And capital A is the area instead of a capital Q as we were seeing previously. All right, so x and y are going to be the depth and the width of the rectangular field, and therefore capital A for area will be the product of those two values, length times width, or in this case depth times width. And the other value, the other equation that often gets overlooked is the fact that the total amount of fencing represented in this diagram is 2,400 feet, linear feet, and that is sort of the perimeter of the fencing that's used here, which is x plus y. In other words, 2x plus y is the total amount of fencing. So we're seeing this equation represented here. Additionally, our area equation, two equations, two variables, we're off to a good start. The recommendation to then take this second equation and solve it for y is a good recommendation. You could also solve it for x, but I think solving it for y is just fine. And then this y value, not that y value, not that color, come on now. There we go. This y value is being substituted into this first equation, so we're replacing that y with 2,400 minus 2x, which gives us capital A equals x times the 2,400 times 2x, and when we distribute multiplication by x, we get the right-hand side of that statement. Now, this is our area equation, and I'm very happy to have this because now the goal, as we read earlier, is to maximize the area. And how do we find a max or a min? Very often, we take the first derivative and set it equal to 0 because we want to know where the top of that hill is. In other words, where the slope of the tangent line will be 0. And so the author has done that, taken the first derivative of the area equation, set it equal to 0, solved, and gotten an x value of 600. The next thing that your author does is to be very mathematical, and I said your author because I'm primarily speaking to my students, but if you're not one of my students and you're listening to this, it's not maybe your author, maybe it's just the author. Or I could just refer to the author as Stewart, as though we're BFFs. The next thing that Stewart does is implements the closed interval method. And the closed interval method says that since we're working with a restricted amount of fencing, the minimum amount of fencing that we could use would be 0. The maximum would be, he's going with 1,200 here, and the fenced area has to have two sides. So in terms of length and width, the x value that we're putting into the equation would max out at 1,200. And he's testing the endpoints of the interval to make sure that even though the first derivative set equal to 0 gave us an x value that was in between the maximum and minimum allowed values for an input value, he's testing the endpoints just to make sure that there isn't a maximum out there. As it turns out, plugging an x value of 0 into the area equation gives an area of 0. Plugging in a x value of 1,200 into the area equation, if all you're doing is going out toward the river and back away from the river, and there's no width to your fenced-in area, the area is going to be 0. So indeed, the x value of 600 is giving us our maximum enclosed area, and you can see that that maximum enclosed area is 720,000 square feet. We could have also confirmed that the x value of 600 gives us a maximum by taking the second derivative, plugging in the, oh, we don't even have to plug in the x value of 600 because the second derivative of our area function is -4. -4 is less than 0, which means it's concave down for all of our x values. The other reason why you might not have done any of that testing, when I said earlier that Stewart went a little bit mathematical, the observation that our original area equation is a second-degree polynomial. In other words, it's a quadratic with a leading coefficient of -2. Notice the -2 in front of the x squared term. That tells me that it's a parabola that's concave down. It's going to have a maximum. We already figured out here that that maximum is going to be happening at the point that has an x value of 600. I would have called it a day right there. Make sure that we're answering the question. Always, before you answer a question, make sure that you're answering the question. That's the solution. How far back do we have to go to get to the question? Still the solution. What are the dimensions of the field that has the largest area? We found out that our x value was 600. So this is 600 and this is 600. We had a total of 2,400 available feet of fencing. We've used 1,200 total here and here. Take that 1,200 away from a total available of 2,400. That leaves you with 1,200 remaining feet there. So you could, on your diagram, label those, and your two answers are going to be 600 and 1,200. And if you're typing those in as free response, sort of fill in the blank answers, make sure that you're typing them into the right spaces for the correct text entry boxes in case there is any discrimination made between length and width or depth and width. We could have also been made aware that that was a maximum by examining the first derivative to the left of an x value of 600 and to the right of an x value of 600, seeing that we're increasing to the left, we were decreasing to the right, and a transition from an increasing function to a decreasing function means, as long as the function is defined there, that we're looking at a maximum. The next thing I want to talk about is an example provided to us about business and economics, but first I'm going to adjust my blinds so that I don't look like I'm in some sort of illuminated jail cell. Let's see if that helps. Much better. Okay. So some vocabulary that you may or may not be familiar with. The three big numbers that we typically talk about in business are cost, revenue, and profit. And of course, the desire, at least numerically, is to maximize profit. So we'll get there. But capital C usually represents a cost function, and C is usually literally a function of number of units that you're producing. Not selling so much, because it's a cost, right? This is money that's going out the door. This is paying to be in business. You've got to pay to have your product produced. Your cost function might also involve some sort of a fixed value, like a rent cost. The cost of rent, or the cost of electricity or internet or water, building maintenance, things like that. Those have nothing to do with the number of units produced, right? You're still going to have that overhead cost whether you manufacture any goods or not. Okay, but let's not go too deep. See, there I go, getting too far in, farther than necessary. So there's a cost function. There's also a marginal cost function, which is going to be the rate of change of cost. In other words, marginal cost is the first derivative of the cost function. If you're not taking notes, you might want to be. I actually typed up notes because I could just copy and paste these slides. I cheated a little bit. My students have access to these slides too. So I just wrote down or copy and pasted all these little bits. So even I took notes on these notes. So I recommend that you do that also. There's also this function p of x, which represents the price per unit. Now, if you've ever had t-shirts screen printed, you know that the cost to produce that first t-shirt is very expensive because the screen printer has to create the screen in order to print that one t-shirt. So the cost of printing your first t-shirt might be $100. But the cost to produce the second t-shirt is only going to cost you, I don't know, $3 maybe. Why? Because I only have to pay to create the screens once. And then I'm just paying for whatever that material is that creates the image on the t-shirt and the t-shirt itself, which maybe is $3, maybe it's $5, I don't know. But if it's $5 per shirt after that, and it was $100 for the first shirt, now in order to create 3 shirts, it's going to cost you $110. Well, your price per shirt is now considerably lower than $100 for the first shirt. So as the number of units that you produce increases, your price per unit might decrease, which is why p of x is a function that describes the price per unit. But that is on the condition that you're selling x units. So again, your price is contingent upon number of units either produced or sold. P is called the demand function, which I always found interesting, although I'm not an economist. I'm just a math guy. Interesting that it's called the demand function. Calling it the price function makes a lot more sense to me as an average person, and we would expect it to be a decreasing function of x. The more units you produce, the lower the price per unit. And notice I didn't say cost per unit, I said price per unit. So that's going to be price to the consumer. Price of a Ferrari, price of a Toyota Camry, right? The more you produce, the less they cost to the consumer because, presumably, the less it costs to the supplier. If x units are sold and the price per unit is p of x, then the total revenue equals, so here's our revenue equation, that's an important one. It is the number of units that you're selling multiplied by the price per unit sold. Number of units that you sold, price per unit sold. And again, that's the revenue equation. Marginal revenue is the first derivative, or the rate of change of the revenue equation. And finally, we put those two things together in order to calculate the profit. Profit is equal to revenue minus cost, period. Marginal function, rate of change of profit, first derivative of the profit function. Would it be a good idea? This is the piece of paper that I held up in front of the camera a second ago. I took notes on the already created notes. If you don't have this slide and you like it, pause, take a screenshot, crop it down, and print it, and maybe just tape it right into your notes. Otherwise, put these notes in by hand. But there's everything from the past, like 3 or 4 slides, all put onto one page. This R kind of slid down a little. Not sure why that happened. Okay, so here's an example, finally. A store has been selling 200 flat screen TVs per week at $350 each. A market survey indicates that for each $10 rebate offered to buyers, the number of TVs sold will increase by 20 TVs per week. Find the demand function and the revenue function. And how large of a rebate should the store offer in order to maximize the revenue? All right, so the scene has been set, right? We've got initially 200 flat screen TVs per week going out the door at $350 a piece. Every time we discount the cost by $10, we're going to sell an additional 20 TVs per week. At some point, that's going to balance out, right? If we decrease the price down to 0, it doesn't matter how many TVs we sell, we're going to be losing money. So there's got to be a midpoint there, and that's what we're going to try to find. So first, find the demand function, then the revenue function, and then determine how large of a rebate in order to maximize revenue. I'm even going to do that in a different color. how large of a rebate in order to maximize revenue. And this was a first question, and this was a second question, and in yellow we've got our third question. Okay, a little sloppy, but you see what I'm trying to do there. I'm trying to highlight what it is we're trying to figure out. The known information, I don't have to highlight that because those are numbers that are up there. The solution says, in order to find the demand function, if X is the number of TVs sold per week, the weekly increase in sales is. So, in other words, if I offered a rebate, the number of TVs that I sell is going to go up. So let's say I offer a $10 rebate on my TVs. How many TVs am I going to sell the next week? Well, supposedly 220. Well, what was the increase then in flat screen TV sales? Normally I sell 200. Now I'm selling 220. The increase in sales would be 20 TVs. That's my new number of sales, 220, minus my original number of sales. So that's what that expression means, X minus 200. For each increase of 200 units, the price is decreased by 10. So for each additional unit sold, the decrease in price would be, this is, make sure that the numbers line up, it's $10 per 20 units sold. So this is dollars, that's on the 10, and this is 20 units. This multiplication yields this fraction, which also yields this fraction. So when you see that 1/2 popping up, or really it's really a negative 1/2, that's where that's coming from. So our profit function, our price function is $350. So right now we're switching into dollars. This is not number of units. This is $350 was the original price. And how many times are we going to implement this reduction? It has to do with our total number of units sold, or a desired total number of units sold, right? Whether this is reality or this is just something that we're trying to forecast. And so we end up with this demand function, which, remember, represents price per unit. So this is if somebody walks into the store and buys it, that equation or that function, P of X, is going to determine how much they're going to have to pay. The revenue function is equal to number of units sold times price per unit. We're replacing P of X here with the 450 minus 1/2 X, distribute multiplication by X, and we get our revenue equation. Drew my line right through my square there. Finally, in order to determine, let's double check on the question. In order to determine how large of a rebate we should offer in order to maximize revenue. If you want to maximize revenue, you better have yourself a revenue equation. And we do. R of X equals 450X minus 1/2 X squared. In order to maximize that, we're going to take the first derivative. There it is. We're going to set it equal to 0. And we'll get a solution of 450. 450 what's? $450, 450 units, 450 units more than I used to sell, $450 more than I used to sell, or less than I used to sell the TVs for. The X value gives an absolute maximum by the first derivative test, simply by observing that the graph of the revenue equation is a parabola that's concave downward, so that X value is taking us to the top of the revenue parabola. But still, that doesn't answer the question, what does X represent? X represents a number of units sold. The corresponding price equation is, so what is the price per unit when we sell 450 units? we can calculate that by taking the 450 units that we're going to sell, dropping it into the price per unit function, and we get out $250 per unit, which is units are TVs, so $225 per TV. Remember that the original price per TV was $350. The recommended new price per unit in order to maximize revenue is $225. So what kind of a rebate do we need to offer? A $125 rebate. Now, the next time you go to the store to buy a TV or to buy a new phone, whatever it is, this often happens on larger ticket items. Technology, I would say, is a really big one. Automobiles also, we see these rebates, and now we see why it is maybe that they're offering these. So in order to maximize revenue, the store should offer a rebate of $125. Great. So that is the end of the slides provided by the author, and now I want to toggle over and talk through some of those homework problems that I plan to assign, and let's see if technology will cooperate today. That went very smoothly. Let me see. So these questions are kind of wide, and I can't zoom in on that very well. So let's just start out with this first question. I have to move a little closer. It's so small on my screen. For each cost function given in dollars, find the cost, average cost, and marginal cost. We didn't talk about average cost, but you're going to have no trouble with that. The marginal cost at a production level of 1,000 units, the production level that will minimize the average cost. And so basically answer the following questions. Thanks for giving us all of that. We could have just said, answer this stuff. Here is our cost equation. Instead of X representing number of units produced or purchased from a manufacturer, we're using the variable Q. That's okay. And what would be the cost to purchase or to have manufactured or produced 1,000 units? We're going to, I'm not going to, you can if you want to, I'm not going to do this. You would take the value of 1,000. What's happening? I can't write on this. That's going to be a problem. How quickly can I fix that? All right, hang with me. Let's see. Can we just bring it up in here? I think maybe we can. And then can I minimize this? This is real BTS that's happening here. Sure. We'll just cover that one up. Oh, this isn't going to help because I can't write on this either. And for my next trick, I remember. Let's do this. Screenshot. Use the screenshot. Full page. Well, looks like we could just write on this. Let's do that. Oh, it's writing. Now it's scrolling. All right, sorry about that. Where were we? Oh yes, we're going to take this value of 1,000, number of units, and you're going to plug that in for Q. I don't know why I have to draw all these arrows. I feel like that way I'm participating. Take 1,000, plug it into your cost function. So said more succinctly, this would, your first answer here is going to be C of 1,000. So that's the cost to produce all 1,000 of those units. What's the average cost? In other words, it's the average cost per unit. You're going to take whatever this value is, and I don't know what that number is because I'm not going to do the arithmetic. This answer, let's do it with a different color. This answer is going to be the cost of producing 1,000 units divided by 1,000. Average cost per unit, in other words. And the marginal cost I want purple. Give me purple. Thank you. This is not working. There we go. This marginal cost will be C prime of 1,000. So you'll have to take the first derivative of the original cost function and then plug in a 1,000, do some arithmetic, use a calculator, whatever you're allowed to use, and you'll have yourself an answer. Oh, that's not good. I missed. Alright, that was just to clear some clutter, free up some space. The production level that will minimize the average cost. The production level that will minimize the average cost. In order to minimize something or find the minimum, we need an original equation. In the slides that we were going through earlier in this video, that was originally represented by this large capital letter Q. In this case, in part B, the average cost function would be, or is really, this is so strange. The average cost function is the cost function, C of Q, divided by Q. Just like finding the average cost of 1,000 units required us to take C of 1,000 and divide by 1,000. So this is your average cost function, which is still a function of Q. So take your, I'm going to keep doing this, I'm going to keep trying to scroll and I end up drawing these little lines. Take the original cost function, divide it by Q, or multiply it by Q to the negative first power. You'll have yourself a new function, and then you can take the derivative of that and set it equal to 0, and you will find the number of units that you need to purchase or produce in order to minimize your average cost per unit. Certainly a valuable number. If you go back to the t-shirt example, we want to minimize the cost that I have to buy the t-shirts for, so that then I can try to figure out the best price then to sell them in order to maximize my profit. Okay, when you take that original C function and you divide it by Q, this is going to become Q squared. This will become Q to the first power. This is going to become 340, but be careful, this is going to become 8,000 over Q, or 8,000 Q to the negative first power. And then you're going to be taking the derivative of that. I recommend that you write it as 8,000 Q to the negative 1, and then you use your normal processes for taking the first derivative. Take the exponent, multiply it out front, decrease the exponent by 1, okay? You'll get negative 8,000 Q to the negative second power. You're setting all that equal to 0. You might want to use a grapher in order to solve that, but you can do it. And the minimum average cost will be found by taking whatever you find as a Q value, rounded to the nearest integer. You'll take that Q value and plug it into the cost function, minimum average cost. So you'll want to plug it into your average cost function. For example, plugging in 1,000 and then dividing by 1,000, and that'll tell you what your minimum average cost is per unit. If a company's cost function is the following, and the revenue function is that, find the production level that maximizes profit. This is such an important lesson. If you're going to be maximizing area, you need an area equation. If you're maximizing volume, if you're maximizing velocity, here we're trying to maximize profit. What are we going to need? A profit equation, profit function. What's the profit function? Profit function is P of Q always equals revenue, the amount of money that actually came in and ended up in the cash register, minus the cost of running the business, the cost function. Profit equals revenue minus cost. Use these two functions. Don't forget to distribute the minus sign when you substitute in for these two functions. Figure out your profit function, take the first derivative, set it equal to 0, find yourself a Q value. That Q value is the number of units that will maximize your profit. It'll maximize your profit. You're only being asked here to find the production level that's going to maximize profit. That was supposed to be a highlighter. There it is. You're only trying to find the production level. You're not actually trying to find the maximum profit. If you were, you would have to take whatever Q value you find and plug it back into your profit equation. But that's not the call of the question here. The toy manufacturer's cost for producing Q units is given by the following function. If the demand for the game is given by this P equals 8.6 minus 1 over 440Q function or equation, how many games should be produced in order to maximize profit? This is such a huge component of the question. We're going to need a profit function. If you're going to maximize profit, got to have a profit function. Well, I know that I don't want to highlight in red. Here we go. Let's write in red. I know that profit is equal to revenue minus cost. And I know, because I've been taking notes, that revenue is equal to number of units sold times the price per unit. And if you want to write that as P of X, I should have done all this in terms of X. Let's just back up just a little bit. Because these questions, instead of using X as the number of units produced, we're using Q. So let me write this as revenue is equal to Q, number of units manufactured, times price per unit minus cost, which here is being given to us as a function of Q. So this expression for P on the right-hand side is going to come in and replace that P, and this function for Q, or for cost rather, is going to come in and replace this. And when you make your replacements, you're going to use parentheses, and the parentheses are important because when you take Q, switch please, no. When this Q gets distributed, it'll have to get distributed to both of these terms. And when this minus sign gets distributed into the cost function, it's going to have to multiply to all three of these terms. So be careful with your signs. Now you got yourself a profit function. First derivative, set it equal to 0. Find the Q value that maximizes your profit. Just glancing at this, and it's going to be a second degree polynomial, so it'll be very straightforward. The numbers are not super nice, but you can do it. Just be careful again with your positives and negatives. Let's see if opening this window gives me a little bit more light. Now that the sun has gone down. Adds a little mystique with the rays of sun coming in. Okay, let's dial this light up a little bit. Right, so when you take the first derivative of that profit function, you'll set it equal to 0, and you'll get a Q value. How many games should be produced to realize that maximized profit? So your answer is going to be a Q value. So whatever you find by taking the first derivative and setting it equal to 0, that's going to be your answer. If you wanted to know the maximum profit, you would then have to take that Q value and plug it into your profit function. Number 4, find the production level at which the marginal cost function starts to increase. Marginal cost function. So step number 1 in this problem is you're going to need to find C prime of Q. That's going to be some new function. Call it whatever you want. MC. So that's your new function, the marginal cost function. Now, what do you want to do? You want to figure out where it starts increasing. What kind of a function is What kind of a highlighter was that? There we go. What kind of a function is this? It's a third degree polynomial. When you take the first derivative of that function, what are you going to have? A second degree polynomial. You mean like a quadratic? I sure do. And is that quadratic function going to be concave up or concave down? Well, when I take the first derivative of this first term, I'm going to get positive 0.0024 q squared. You're going to have a positive coefficient on your squared term. So now you tell me, is your parabola going to be concave up or down? It's going to be concave up. So I didn't give you much time to answer that question. So, well, regardless of where the parabola exists, it's going to be concave up, and we're trying to figure out, and remember that this is your marginal cost function now that is parabolic. You want to figure out where it starts to increase. I would say that it's fairly obvious that we're decreasing on this interval. Here is your minimum, and then we start to increase. And the question is the production level at which it starts to increase, which means you're looking for the Q value at that point. You don't need to know the Y value, the actual marginal cost. We only want the production level, so again, you're only looking for the Q value at that point. So you're going to need then the first derivative of your marginal cost function. You'll take that and set it equal to 0, and you'll find Q. So actually, it's the second derivative of the cost function or the first derivative of the marginal cost function that you're setting equal to 0. And the last question in this homework set, well, perfect. It's about selling televisions, so we don't have to do that one. Rebate, if the company experiences a cost of that, how should the manufacturer set the size of the rebate in order to maximize its profit? I'm going to leave that one to you. We already spent so much time on that in the in Stewart's notes that I'm going to leave you to fill those in and wrestle with the tail end of that problem. Hey, thank you so much for joining me talking about these optimization problems. I hope they were helpful, and don't forget, whatever it is that you're trying to optimize, you need a function that describes that event, whether it's area, profit, marginal cost, etc. You need that function before you can take a first derivative and set it equal to 0. Also be mindful that if whatever your initial function is, like a cost function or profit function, etc., if it were to be a fourth degree polynomial, for example, when you take that first derivative, you're going to get a second degree, or if you're starting with a fourth degree polynomial, you're going to take the first derivative and get a third degree. That third degree polynomial, when you set it equal to 0, is going to end up having potentially, am I saying this right? No, all you have to do is start with a third degree poly, take the first derivative, get a second degree polynomial, set that equal to 0, and you're going to get 2 answers. So you'll have to be careful and take the extra time to decide which one of those x values or q values is resulting in a local minimum and which one's resulting in a local maximum. Again, if I'll just draw a little sketch, I'll use this white space that's here. If your original cost function, for example, were a cubic, then your marginal cost function would be a quadratic. And when you take this and you set it equal to 0, certainly when you take a quadratic and set it equal to 0, you're going to get 2 solutions. Something tells me that this is going to have no solutions. Let's make this a minus sign and a minus sign, and we'll make it a 22x, so that this is minus 22. There we go. That ought to have 2 real solutions. Which one of those is going to be an x value that's giving you the local max, and which one's a local min? Pay attention to the domain, maybe. Maybe one of the x values that zeroes that out is a negative number, and in fact, it will be. It's going to be negative square root of 22/3. I don't think you're going to be producing a negative number of units. So That's not even in the domain, so you can throw that one out, so that'll be helpful. But even the one that is in the domain, please take the time to confirm that that's going to be a maximum or a minimum, or are we seeing increasing or decreasing after that? See, I told you I would struggle to keep this short, but hopefully it was helpful. I look forward to you joining me for another video in the future. Be well.